Hello again and welcome. During the last video I mentioned I was going to take the new Fluke 87V and compare that against the last one that I had tested. This is the meter that had failed at 1.5 kV. If you look at the circuit board, you can see this is a revision 10. Looking at the differences between this old board and the new one, the PTC is definitely different. The new one has a green color to it where this one's black, and I believe that these are actually manufactured by different companies. Yeah, they are. The MOVs, I believe, are made by the same company. They are a little different. They have the same part number, but the package is slightly different. You know, the resistor looks identical, and all the components down here appear to be the same. So I can't really tell you, looking at this thing, why it broke down at such a low voltage. It seems like it should just be as robust as the other meter. One thing I did notice are these two resistors, this one here and the other one below the fuse. There's a test that's performed per the IEC standard where essentially you remove the fuses and then you apply a voltage which is 2 times over what the maximum rating of the meter is. And what happened with the brand new meter is these two resistors were hot enough where you saw smoke coming out of the meter. Those appear to be a higher wattage part. If you look at the layout, they actually had to change the spacing of the pads to install those new resistors. So that's one of the differences between the circuit boards. So I'm curious with this size resistor, which is basically a 1/2 watt, and I believe that these are a carbon comp resistor, and I'm wondering now if these could actually handle that kind of power dissipation for a minute. So I have a few different resistors I'd like to test. The Bryman on the left will be measuring the voltage, and again that's using this small attenuator that I made. The meter on the right is going to be looking at the body temperature. So what I'm going to do is just turn this on. And you can see we're putting roughly 2,000 volts across that resistor right now. And we can see the package starting to heat up. I'm just going to let this sit for a minute and let's see how hot this device gets. Now granted, the resistor that's inside of the meter doesn't have the full 2 kV across it. There are additional clamps in there, so you know, it's actually going to be a few volts less than that, but it's going to be negligible. So there you go, about 90 degrees. We never saw any smoke coming off of this part. It's actually quite hot right now. But again, there's no physical signs of any damage to it. Now compare that with a part like this. This is also a 1 mega ohm part. Unfortunately, I don't have any thermocouples that are real low mass. Alright, let's give it a try again. This will be for 1 minute. You can see at 15 seconds we're already exceeded what the other resistor had. 144 degrees Celsius. 30 seconds into it and we're at 160. 45 seconds, we're almost at 170. There you go. Looks like it survived. I don't know if it'll show up on the camera, but there's a dark spot right down the center of it. I'm not sure how much longer it would have survived like that. I almost thought I wasn't going to be able to run this next test, but I've got some old carbon comp resistors. You can see this one's not the right value, but this is the correct body style. So I was going through my stash and I ended up finding a 1 mega ohm carbon comp resistor. And you can see we're at 2,000 volts. Temperature is already at 70 degrees Celsius. If anything, it almost looks like it's cooling down, but I can see the resistors changing colors. The green is no longer green. Let's just go ahead and we'll have a look at the resistance. There you go, look at this. So it now measures 2.3 mega ohms. So we've damaged this component. Let's just have a look at that carbon film part. You can see this one still is basically spot on at 1 meg. And again, this is our carbon comp 1 watt, and again you can see it's also spot on at 1 meg. So yeah, we definitely damaged this little resistor. So now I'm wondering if the resistors that were supplied with the original meters would survive this test or not. I mean, it's definitely what they look like, is an old carbon comp half watt body. So if we look at the bottom of the circuit board, you can see it's marked 2002 Fluke. So it's 2018 now. So this meter's been being produced for at least 15 years now. Again, the serial number on this starts out with a 10. Compare that with the new meter. This one starts out with a 40. So this meter is quite a bit older. So what I'm wondering is, did this meter conform to a different IEC standard than what the new meter does? So if we look at the back of the meter, you can see it's marked Made in USA, and it's been certified by basically everybody. Well, I don't see much of a point in just heating these up just to destroy them, so I'm probably not going to do that. This is the area up here that was damaged. I had actually cracked all the cases on these devices. I've designated those 4 diodes as D1 through D4. D2 through D3 are marked JY. I believe those are a BOV 199. Those are an 80 volt 200 milliamp device. D1 is marked F2, and I believe that's a 5237 8.2 volt Zener. The custom IC that's located on the board here outputs a voltage, and that goes through this 1 mega ohm resistor, and that voltage is slightly lower than what D1's clamping voltage is, and the idea is that reverse biases D3 and D4, and that minimizes the leakage current through this path. So if a transient comes through that's positive, of course that works its way down through the switch, it would go through this side or this side of D3 or D4 and then be clamped by D1 back to ground. If the transient goes negative, basically it goes through the 2 junctions of D2 and then back through D4 or D3 and then return through the input here. So what I'd like to do is replicate this circuitry on our little test board, which I've gone ahead and done. So at the front end of this I have our 1K ohm resistor, and that's followed by this fairly large PTC, similar in size to what's on the Fluke 87V. And then that goes through 2 MOVs that are in series. And then what I have is 2 BOV 199s along with our 5237. So you can see the 199 here and here. So I basically form this loop. So I'm going to be using our attenuator to essentially look at this side of the clamp. So currently I have this jumper removed. So basically what I'm looking at is the MOVs doing all the work. You can hear our power supply is getting loaded a fair amount right now. The MOVs are definitely starting to clamp. So we're at about 1430 volts right now. I didn't have the exact MOVs that the Fluke 87V uses. Again, once the clamp is enabled, this should only get to roughly the 8.2 plus the 0.7 drop of the diode. So again, this board is fairly flexible. So I have another TVS on here that I looked at prior. What I'm going to do is just enable that. I'm going to go ahead and turn on the AC output of our transient generator. What we'll do is just have a look at that with our Bryman meter. You can see we're at 240 volts. So right now this PTC should be quite hot. Yep, and you can see the output is actually at 13 volts. The majority of that voltage is being dropped across this PTC. You can see 222 volts here. And you can see looking across our resistor is roughly 5 volts. And again, the temperature of this device is quite high right now. What I'm going to do now is just turn off the AC output, and I'm going to select this other clamp. So inside of the real meter, that clamp is actually there to protect this IC when it's being used to drive current back to this input pin. So essentially if the meter's measuring resistance, for example. So now I'm just going to re-enable our AC, and let's just see if this still clamps our voltage. There you can see it. So 8.9 volts. So let's have a look across our Zener diode, and you can see 8.1, and our other BAV 199 should be roughly 0.7. You can see it's about 0.6. And again, the majority of the voltage should be dropped across our PTC. There you have it. So 225 volts or so. Let's go ahead and disable this again. What I'm going to do is reverse these two leads. Again, this is a full rectified AC output coming out of the generator. So it's essentially DC with a lot of ripple. So again, the way we just tested it, the current flows through the PTC and the 1K, through our switch, back through one of the diodes here, through our Zener, and then back to the return path. When I flip the polarity, it's going to go through this diode, back through the switch. So let's go ahead and turn it back on. You can see the voltage drop is quite a bit less. It's at basically 2 volts. And that's because we don't have the effects of that Zener anymore. It's basically just the different diode drops. So if we look across just the one diode, you can see roughly 1 volt. Again, that's the 2 diode junctions in series. And let's look across our other diode here, and there's our 0.7. So this all seems to function just fine. So our test board is configured to simulate the Fluke 87V's front end right now. You can see on the oscilloscope this is 500 volts per division right now, or 2 divisions up. Again, we'll apply 5 transients, both positive and negative. Then we'll go back and test all of our diodes. That one's still fine. Let's check this one. That one looks okay. And this one is okay as well. And this one looks fine as well. So you can see I've changed our setup just a little bit. So I now have this secondary high voltage probe attached to the output of the clamp. The transient generator is still set for 1000 volts. What I'm going to do is just apply a couple more transients. Alright, so again we can see the oscilloscope set at 100 microseconds per division and 500 volts per division vertical. You'll notice as soon as the transient fires, this is our clamp engaging, and then as the transient decays, of course the output across the clamp also decays along with it. Okay, you can see we're still at 500 volts per division. We're now 3 divisions up, or 1.5 kV. And again, we'll go ahead and apply 5 transients, both positive and negative, and retest our diodes at the end of it. Alright, so we'll start with our Zener diode. That looks okay. This is one side of our BAV 199. That one looks good. Let's try the other leg. That looks fine as well. Let's look across our other 199. That one looks alright. And let's check the other junction. That one seems fine as well. So it doesn't appear that we've damaged it. You can see we're now at 1000 volts per division, still 100 microseconds, and we are currently 4 divisions up, or 4 kV. Again, the full width half height, or 2 divisions up, is roughly 100 microseconds, or 1 division. Again, we'll be applying 5 transients, both positive and negative. It really doesn't change the wave shape at all. Again, we'll just go ahead and invert this, and we'll apply 5 more transients. Again, this is our Zener diode. That one appears to be fine. This is the one leg of the BAV 199. This is the other one. Let's have a look here. That one looks good as well. Let's have a look at the last BAV 199. That looks good. And that leg looks good as well. So that's all the way up at 4000 volts. And no problems with this proto board at all. Again, the MOV shouldn't really even be coming into play here because all the clamping is done over here. Again, the thermal response of the PTC is going to be way too slow for a transient like this. So basically what we're dealing with is the DC resistance of the PTC in series with the resistor. So that combined resistance is where all the voltage is being dropped at. Alright, so with our little test board doing so well, I think what I'd like to do is have a look again at the original meter. All I'm going to do is install our little rotary switch. We'll set this roughly to the off position. I'll go ahead and install a little battery. And we'll use our second Bryman here to measure the output voltage. Basically what we're looking for is the output to turn on. It'll tell me that we're in the resistance mode. Oh, right there. Alright, let's have a look across our Zener Diode. And you can see it's reading 6.7, 6.8 volts. And again, that's driven off of this resistor here, I believe. Let's just have a look. Right, so about 7.5. So this is the highest that this chip is able to put out. Right, so off to my left you can see I have one of our high voltage power supplies out. It's attached to this meter on the left, and again this is going through this ×10 attenuator. Now that we know that the switch is in the proper position for the resistance mode, we'll just go ahead and remove our battery. You can see our power supply essentially just folds back. Let's have a look across our Zener. So it looks like the clamp is doing its job. Again, this power supply is only capable of putting out about 200 microamps. I think what we'll do next is go ahead and remove our switch. So that clamp now is deactivated. Alright, so this meter is looking at the current output off of our power supply. And again, the power supply is rated for 200 microamps. What I want to know is basically where it switches at to see if our MOVs are working correctly. There's 1.8 kV. And that is the limit. So it doesn't look like the MOVs have been damaged. The other thing, nothing broke down up in the front end here. Alright, let's go ahead and have a look across some of these parts. So currently you can see I'm putting out roughly 415 volts or so. You can see it's only dropping about 2 volts or so. Let's have a look across our resistor. Alright, let's look across our MOVs. You can see we're loading it down a little bit, so about 340 volts with the meter across it. Again, let's go ahead and turn that up. There's about 830 volts across them right now. Let's check our common point. It's about 160 volts or so there. Also, I'm going to do is select this back to the resistance mode. Again, this will enable one of the clamps. And I'm going to attach our transient generator. So now what I'm going to do is enable the AC output. And let's go ahead and look at the voltage drop across the PTC. You can see about 253 volts right now. Again, I'm assuming that part's getting pretty hot. Let's look at the voltage drop across our 1K. You can see about 5 volts. So the other clamp is activated in the diode mode. Let's go ahead and enable that. And again, let's turn on our output. And I can tell you that's engaged right now because I can smell the PTC heating up. So let's have a look. Yep, again, so 254 volts being dropped across it. And again, about 3.7, 4.7 volts across our resistor. Now let's turn that back off. So to test the other leg of the diodes, what we have to do is reverse the polarity. Again, we'll enable our AC output. See the meter readings over range. And again, let's look at the voltage across the PTC. And again, about 260 volts. Let's just switch it over to the ohms mode. See, it's reading a negative 1.4 mega ohms. And again, let's look across the PTC. And again, about 260 volts. Alright, let's just do a real quick sanity check. So again, switch it to ohms. And this is with a 1 mega ohm resistor in there. And let's just put our 50 ohm. You can see that's fine. Let's just switch it over to millivolts. Again, this should be roughly 20 millivolts in the center. You can see it looks fine. So that little bit of testing hasn't done anything to it. Alright, so you can see I have our second high voltage probe out. Currently the two are attached in parallel, connected to our transient generator. And again, we are at 500 volts per division currently. And you can see the red and the yellow traces overlaid. Those are our two probes. And again, this is 100 microseconds per division. So you notice I have the rotary switch removed. So our secondary clamp is not being activated right now. So currently what we have is the PTC in series with our surge rated resistor in series with the MOVs, and that's what's going to make up our clamp. So I've set our transient generator for 2000 volts peak. So our homemade probe will be looking at the input voltage to the meter, while the Tektronix probe is looking at the voltage across the MOVs. Again, we'll just give it a single transient. Let's see what this looks like. This is not what I would have expected to happen. So again, our scope is at 500 volts per division. You can see we're 4 divisions up right now. So that is 2000 volts peak, what I would expect. But the MOVs, on the other hand, don't seem like they clamped. Let's just go ahead and turn the generator up even higher. So this will be roughly 4000 volts. See, on our scope we are now 4 divisions up, or 4000 volts peak. And across here you can see the Tektronix probe. This will be the 5th transient. And so it looks fine. Well, as you can see, there's no signs of any of this breaking down. Let's just go ahead and give it another 5 transients. I'll bring the camera in a little closer. There you have it. That's 5 more transients. No sign of any breakdown. Again, that's at 4,000 volts peak. As you can see, I put the cover on, and that's basically so I could line up the switch. So it's currently set for the resistance mode. The clamp will actually be engaged now. And what I'm going to do is again apply 5 transients, both positive and negative this time. And I'm keeping this at 4,000 volts. Just going to move the camera in a little closer. If something does break down, we should be able to see it. Again, what's kind of odd about this is when I ran this test, it actually cracked the components. So if something does go wrong again, this is what I would expect to see happen. Alright, here we go. 5 transients, 4,000 volts. See, our Tektronix probe is basically at ground, so the clamp definitely activated. It's looking real good so far. There's one more transient left. Alright, what I'm going to do is reverse the polarity. And this actually changes the path of the current through that clamp. Again, we'll apply 5 more transients. So I was looking at this, I'm pretty concerned. You can see essentially the 2 probes are on top of each other. I was like, crap, something really has gone wrong. But of course we changed the reference for this other scope probe as well. So the 2 are going to track. What I'm going to do is just go ahead and apply another 5. What I'm going to do now is just rotate our switch to the millivolt setting. And we'll go ahead and apply another 5 transients. It basically engages that second bob 199. Alright, and again, I'll reverse the polarity. And we'll just go ahead and give it another 5 transients. Okay, that's it. Alright, let's have a look at our diodes. Again, this is our Zener. Doesn't look like it's leaking. And it's definitely conducting this direction. That one looks fine. See, that one looks okay. And that one looks fine as well. So it doesn't look like we've damaged anything. And so I just gone ahead and installed the cover. And we'll attach a battery. So the switch is a little off. We'll turn it to the off position. Should get our F87. Alright, so again, I'm sure that the voltage inputs are just fine. This would be 2.5 volts. And again, this is 2.5 volts. that's DC coupled. Should be 5 volts. And in the millivolt range, again, this should be roughly 20 millivolts. And in resistance mode, again, this is with an open. And normally what you'd see when these fail is with an open like this, it'll read some resistance. Let's just go ahead and we'll put a 1 meg across it. That looks fine. And again, let's just put a 1 ohm. That looks fine. This is a 100 ohm. Alright, let's go ahead and install our switches. And we'll set this to the capacitance mode. Let's go ahead and rel this out. And this will be 150 picofarads. This will be 1 nanofarad. This will be a 0.1 microfarad. And let's try it in diode check mode. Again, this is with an open. Here's with a short. You want to see a diode, so this will just be a single diode. Alright, so you can see that the meter has survived that just fine. So again, that's 4,000 volts peak, 5 transients, both positive and negative. Again, this meter was damaged at 1.5 kV. Of course, there's some things that have changed about this meter. It doesn't have any of the original components that made up that high-speed clamp that I had damaged. So this meter has 3 brand new BOV 199s, along with a brand new 5237 Zener. Again, the MOVs, the PTC, the high-rated surge resistor, all those are original. It's just the high-speed clamp was the only thing that I've actually changed on this meter. And the way that they failed, where the cases were actually cracked, I'm just quite surprised that it's behaving completely different this time through. So the next test I'm going to run is I've got the transient generator turned all the way up. It's just shy of 6,000 volts, and again we'll be running both positive and negative pulses, and we'll do this with the meter set to each mode. So again, this will be 5 transients, about 5,800 volts peak with a 2 ohm source impedance. Alright, let's just do a real quick check. See, it's reading an open. Alright, go ahead and invert the polarity. And again, we'll apply 5 more transients. Let's just switch it to ohms. You can see with an open, let's just try it with a 50 ohm. See, that's fine. This will be a 1 meg. Looks fine. Let's try it in capacitance mode. Again, this will be a 0.1 microfarad. Looks good. Switch it to millivolts. And again, this should be roughly 20. That looks fine. Diode check. This is with an open, and here's with a short. Looks fine. And DC volts should be 5 volts. Looks good. This should be 2.5. Looks good. In AC mode, this should be 2.5, and this should be 2.5 as well. This should be roughly 70 volts. And this should be roughly 60. Alright, I'll go ahead and finish functional testing the meter, but it looks okay. One of the things about repeating this test with this particular meter, again, now both meters surviving everything that this transient generator is capable of putting out. I really don't have a flyer in any of the data. Again, if you go back and look at the original data that I collected where I ran the $50 meters, it came down to 2 meters in amprobe AM510 and a Fluke 101. That amprobe AM510 was damaged with a 5.8 kV transient. And again, I used that criteria to set the upper limit for this transient generator. Basically what I'm suggesting is if a meter survives everything that this transient generator puts out, I'm calling that meter robust. And I basically classify those meters differently than the ones that fail with this generator. Again, this has nothing to do with safety. And I would say if you're trying to determine if a meter is robust or not before buying it, what you're looking for is for the meters to have passed the IEC 61326 standard. Again, that's the EMC standard, not the safety standard. I'm not really sure how to summarize this. Again, when this meter on the right had failed at 1.5 kV, it had actually fractured the case of the 3 BOV 199s. It also damaged D1. The fact that there was enough energy in this area to crack the parts is what really throws me. That would have almost meant that this area here had to break down. And again, the test I just ran, it doesn't look like there's any signs of problems with any of these parts. The other thing too is after replacing all these components, of course I've pushed the meter much higher than what it was originally damaged at, and again, we're not seeing any problems with it. So a few things to note is that the circuit board in this area where the clamp resides, that doesn't appear to have changed between these two meters. And while the PTC brand does appear to have changed, and the MOVs do look like a slightly different package, but they appear to be the same manufacturer and part number, I don't believe that that really has any effect on this. We could say that maybe there was a defective component in it, but again, that really doesn't make a whole lot of sense. Even if the parts were shorted, the meter wouldn't have worked functionally. And if a diode, for example, had opened up, again, I'm not going to see the parts fracturing like what I saw. It just basically points to something arcing. And it's possible maybe there was some contamination on the circuit board that caused it to break down. Again, when I have these meters apart, you can see I take a fair amount of care to keep everything clean. It's possible there was some kind of an etching problem that caused a burr on one of the traces, and maybe that jumped. However, when I look at the circuit board itself, I don't really see any signs of anything like that going on. Obviously, I didn't modify the circuit board, and it didn't break down this time. So that, again, points to something possibly on the outside of the circuit board. Unfortunately, I don't think we're ever going to know. Again, the meter behaves completely different now, and the only thing I've really done is had the meter apart. Obviously, it's been cleaned, and I've changed out 4 diodes. And I believe I've replaced those with what the OEM parts are. Of course, they would have a different date code, but they should have the same performance of the original parts. So I don't really know what to make of it. I've gone ahead and updated the spreadsheet to include this meter where I've made the repairs, and I've repeated the testing with it. Well, that's going to be all for now. I hope you Fluke fanboys enjoyed this series. I don't think I'm going to do anything more with this meter. I'm surprised how many new followers this channel has picked up. It's good to have you on board. I hope you enjoyed the series. Well, that's going to be all for now. Until the next video, later.